So today's lecture is going to discuss the joint distribution. If you want to look this up in your book, it should be in chapter 6. This is where we discuss two sets of topics. The first set of topic, which is shown by number 1 here, with all the subcategories A, B, C, and D. This part discusses how to deal with more than one random variable. We will first discuss the concept of joint probability distributions, so representing the probabilities for two random variables. By the way, this applies also to more than two random variables, but in the scope of our course here, we will only discuss the case of two random variables together. So the first part discusses how you can represent two random variables in terms of probability of occurrences. That's called the joint probability distribution. Then we'll discuss how you can get back to the probability distribution of each random variable separately rather than representing them jointly. We call this the marginal probability distribution. We'll see how to get one from the other. We will also discuss, since we have more than one random variable, there might be some dependency between them. And in this case, we will discuss the conditional distribution. So the distribution of one random variable given a particular value for the other random variable. That's called a conditional probability distribution. Last but not least, today we will discuss independence. For the next lecture video, we will discuss the covariance and correlation, as well as the linear function, so combining more than one random variable together in a linear relation, so summation with some multiplication with constants. And last but not least, we will also discuss the general functions of random variables and how they can be represented in terms of distribution as a function of the original distribution of the random variable. These three topics, the last one shown in black, will be discussed in the next video lecture. So let's start. What do we mean by joint probability distribution? This slide is meant to give you a quick introduction. What do we mean by this concept? So mainly the idea here is it happens a lot. First of all, why do we need this? It happens a lot that we have to deal with more than one random quantity. And if that random quantity is represented in terms of random variables, then we deal with more than one random variable. And as I mentioned in the previous slide, we are restricted here in this course to the case of two random variables. However, in reality, and using the same concept, it can be extended to more than two, so 3, 4, 5, 6, and so on, but that's outside the scope of this course. Okay. So let's take an example that we have looked at before. Classification of transmitted and received signals. Remember that we discussed earlier a problem in one of the earlier chapters in discrete random variables, the problem where you have the signal arriving at your, the signal that you receive at your phone represented by a quality indicator, which is like the bars that you see the signal with, right? And let's call that the random variable X. The other random variable, okay, let's say we are discussing the number of signals that you receive with low quality. So basically, you have two received signals. One of them is the number of high quality, two random variables. One of them is counting how many signals you receive with very high quality. Let's say you have multiple cell phones and you are counting how many of them are receiving signal with very high quality, so 3 bars. The other random variable is counting how many of them are receiving very low quality, so that's like 1 bar. And you are not counting the 2 bars case. So these are the two random variables. X is counting high quality signals, Y is counting low quality signals, number of low quality signals, okay? So in that case, you are dealing with two random variables together. And if you want to represent what is the probability that I will have 3 phones with high quality, 1 phone with low quality. So that's the probability that X is equal to 3 and Y is equal to 1, right? Or what's the probability that I will have equal number of phones having high quality and low quality. So in that case, you are looking for the probability that x is equal to some value a and y is equal to also the same value a. So the probability that both random variables are equal to each other, right? And so on. So you can be looking for joint probabilities of joint values of the random variables. Another example is in the continuous case, for example, if you have a product with, let's say, a metal sheet, and it's rectangular, and the width is x and the length is y, and both of them can have some randomnesses, right? So you are looking for the probability that x is greater than 10 centimeters and y is less than 2 centimeters or whatever, right? So some joint probability. Of course, for the case of continuous, we have to deal with ranges on x and y. Cannot be, again, a single point, because a single point will give you zero probability, okay? So in general, we are dealing with the cases where we are interested in probabilities that can be expressed in two random variables, x and y, which indicates the probability that x takes some value x and y takes some value y. We call that the probability, the joint probability that x is equal to some value x and y is equal to some value y. If this is discrete, we call this the joint probability mass function. If this is continuous, we call this the joint probability density function. Just again, out of consideration of the fact that the students who are taking this course might have been exposed to calculus of multiple variables, particularly able to do multiple integrals. Some of you are not yet. Some of you are taking that course right now. So out of that consideration, and without loss of understanding the whole concepts, we will focus only on the case of discrete joint distributions. So the scope of what we will discuss today and what we carry in this course is going to deal only with the case of discrete joint distributions. So we'll generally be dealing with joint probability mass functions. So let's look at an example here that represents something that we have done before. I think it was part of when we discussed the probabilities of joint events in chapter 2. We have discussed this problem, but we have not looked at it from a random variable point of view, which is not that much different, except that the values of the random variables are numeric, right? So let's say that x is the number of bars of signal strength that you receive on your cell phone. So that's an indicator of how strong is your cell phone signal. And y represents the number of times you have to repeat the name of a city until the automatic recognition system recognizes that. So this problem assumes that you are talking over the phone to some automated system, and you are trying to indicate which city you are trying to reach, or which city you are checking on, and the system is recognizing the name of the city automatically. If you have a strong signal, there should be a tendency that it will be recognized from the first time or the second time of repetition. If you have a weaker signal, there should be a tendency. Again, I'm saying tendency because this is not a deterministic relation, right? If you have a weak signal, then there should be a tendency of the system that you need to repeat the name of the city more than once in order for the system to recognize automatically which city you are mentioning. So y is the number of repetitions. That's what you see on this direction. So can take a value 1, repeat the name only once. You have to say it twice until recognized. You have to say it 3 times. You have to say it 4 times until recognized. And x is the number of bars. So you have 1 bar, weak signal, 2 bar, medium signal, 3 bar, very strong signal, right? And then the values that you see here are what we call the joint probability mass functions, or the joint probability distribution of x and y. So for example, the 0.15 that you see here says that the probability that you have a 1 bar in your phone and you have to mention the name of the city 4 times until recognized is equal to 0.15. For example, this one. This is the probability that you have 2 bars in your cell phone and you have to mention the name of the city 3 times until the automated system recognizes it. and that will have a probability of 0.1. Of course, you can see that if we sum all these probabilities together, this represents all the possible cases. So 1 with 4 repetitions, 1 bar with 3 repetitions, 1 bar with 2 repetitions, 1 bar with 1 repetition, 2 with 4, 2 with 3, and so on. So the combination of all possible cases and the addition of their probabilities should give you a value equal to 1. So keep that in mind, that the sum of all these probabilities for joint distribution is also equal to 1. So that's similar to the case of single random variable. Okay. So now we just gave an introduction. What's a joint distribution? Now we are going to look at the properties of joint distribution. Very similar. So again, it's represented by the small f of x and y. Now two random variables instead of just being of x or of y only. For the case of a single random variable, for the joint, it's two random variables here. And we also add this part as subscript of the random variable. So f, x and y of the two random variables, x and y. Here, the small, because these are the values. Here, the names of the random variables, capital X and capital Y, right? Again, it's a distribution, so you can know that its value is always greater than 0, cannot be negative. It's a probability, right? And the sum of all probabilities, in this case, the joint probabilities of x and y, over all possible values of x and all possible values of y should be equal to 1, as we mentioned in the previous table. If you add all the values of the joint distributions, the joint probabilities inside the table, they should give you 1. That's again very similar to the case of single random variable. And since we are dealing with mass function, the discrete case only, then the meaning of the f, the small f of a certain x equals x and y equals y is simply the probability that the random variable x takes the value x and the random variable y takes the value y, right? Joint probability mass functions, again similar to the other case, wherever you have joint values of x and y that is not among the ones that have a probability given to you, then you assume that that is equal to 0, similar to the case of discrete random variables with single random variable as well. So it's the same thing here. Okay. Here's an exercise. Show that the following function satisfies the properties of a joint probability mass function. So what are the properties of a joint probability mass function? That f x y of x and y, right, has to be greater than or equal to 0 for all possible values of x and y, and that the summation over all possible values of x and y, f x y of x comma y, should be equal to 1. So let's see. These are the possible values, the joint possible values of x and y. So it can be that x is equal to 1, y is equal to 1, and the probability for that is 1/4. X is equal to 1.5, y is equal to 2, and the probability of that is 1/8. 1.53, and the probability is 1/4. 2.54, and the probability is 1/4. 3, 5, these are the values of x and y, and that these two values occur together when with probability equal to 1/8, right? So the first thing is, for all the possible values of x and y here, we notice that all of these are greater than 0. So none of them is negative. So the first condition is true. The second condition, the sum of all these probabilities, because these are the probabilities of possible joint values of x and y. So you add all of these together, right? And when you add them together, the sum is going to be equal to 1. So the second condition checks out. 1/4 plus 1/4 plus 1/4, that's 3/4, plus 1/8 plus 1/8, which is 1/4, that's 4/4, which is equal to 1. So the sum over these is equal to 1, which means that the second condition is true, and this means that it satisfies the conditions of a joint probability mass function. Okay. Second part asks you for some probability. So what's the probability that x is less than 2.5? We have done this example before. I'm gonna do a couple of these and then move on. So what's the probability that x is less than 2.5? So x is less than 2.5 means that we are dealing with this range, right? And then the other one says y is less than 3. So y is less than 3 means we are dealing only with this range, right? Correct? So when we say this and this, it means the intersection of both of them. So that's the intersection. What is the probability of this intersection? It's the sum of the probabilities inside, right? So that's basically equal to 1/4 plus 1/8, which is 3/8, right? Let's look at another request. What is the probability that y is greater than 3? So when we say y is greater than 3, I'm going to do it with a different color, right? So let's go. Y is greater than 3 means we are dealing with this part. Any specifications on x? No. Then that's it. So the probability that y is equal to 3 is this whole region, right? So y is equal to 3 regardless of what's the value of x. Sorry, y greater than 3 regardless of what's the value of x, okay? So that means it's again, this is equal to 1/4 plus 1/8, which is 3/8. Let's take another example. What is the probability that x is less than 2.5? X less than 2.5 means we are dealing with this region, right? Any specifications on y? No. Then we take the whole region because that's what satisfies the probability that we are looking for. And this will be 1/4 plus 1/4 plus 1/8, which is equal to 5/8, right? And so on. So that's quite like a quick exercise to show you how to deal with joint distributions in terms of calculating probabilities of certain regions or values of the variables. Let's look at now the second point that we mentioned at the start of the lecture. So we said we will first understand what's a joint distribution and learn how to deal with it. And then the second point was, how can I go from the joint distribution of x and y? So how can I, knowing the joint of x and y, this is known to me, how can I find only the marginal, so the probability of x only, the distribution of the random variable x only, without caring about y, or the probability of the random variable y only without caring about x? We call these marginal distributions. Okay, so the other one was called joint distribution. This one is called marginal distribution, right? So how can I get from the joint to the marginal? It's very simple. If I have the probability of x and y, then if I want to get the marginal of x only, I sum over all the possible values of y. So if I want to get the marginal of x, this is equal to the summation of the joint, right, over all possible values of the random variable that I want to get rid of. I want to get rid of y, so I will sum over the values of y, right? Mathematically, we represent this by saying we sum over the region specified by the values of y, right? So this region is going to be across the all possible values of x and y, but we sum over all possible values of y only, right? Okay. Similarly, if I want to get the fy of y from the marginal, then I sum over all possible values of x. We call this mathematically the region specified by x, but it means summing over all possible values of x, the joint of x and y, right? This will become clearer as soon as we do an example, which is coming in the next slide, right? Again, that's a definition that I've just wrote in the previous slide. If you want to get the marginal of x, you sum over all possible values of y. If you want to get the marginal of y, you sum over all possible values of x. And we call that the region specified by y and the region specified by x, okay? Now, how does that really happen? Let's take this example, okay? Again, back to the example of x represents the number of bars and y represents the number of times you have to repeat the name of the city until you get the system recognizing it, right? Now assume, for example, that I want to get fy of y. So what does this mean? What's fy of y? I want to get fy of 1, fy of 2, fy of 3, fy of 4, because these are the possible values of y. Y can take which values? Y can take the value 1 or 2 or 3 or 4, right? I want to get the probability that y is equal to 1. That's fy of 1. I want to get the probability that y is equal to 2. That's fy of 2. Probability that y is equal to 3, regardless of x. So I don't care about x, right? And this is what we call the distribution of y. And because here we are dealing with joint, we call it the marginal distribution of y. So the distribution of y alone without caring about x, right? This is what we called in chapter 3 the probability mass function of y. So that's what we need to get here, and we get rid of the x. How do we do that? So y equals 1, for example. Okay, if I want to get y equals 1, where are the probability? How can I calculate the probability that y is equal to 1? Simply, okay, this is a case of y equal to 1. This is also another possible case for y equal to 1. This is another possible case for y equal to 1, right? And these are the only cases where y equal to 1 happens. So how do I calculate the probability? This or this or this. I add them together. It's not this and this and this. It cannot be that y is equal to 1 and x is equal to 1 occurring with y equals 1 and x equals 2. It's either y is equal to 1 and x is equal to 1, or y equals 1, x equals 2, or y equals 1 and x equals 3. So these are all the possibilities of y to be equal to 1. So in order, and they occur mutually exclusive, cannot happen together. So the probability that y is equal to 1 is the sum of those probabilities. So you add those values to get the probability, the fy equals 1. Similarly, if I want to do this for the x case, so if I want to calculate fx, right, then this is fx when x equals 1, fx when x equals 2, or fx when x equals 3. These are the possible values of x, right? Can be either 1 or 2 or 3, right? So if I want, for example, to calculate fx of 2, then I will look for the cases where x can be equal to 2, regardless of the value of y. So these are the possible cases for x to be equal to 2. So I add them together, and the result of that is going to be the fx of 2. Similarly, I will do it for the case of 1. Similarly, I'll do it for the case of 3. And then by getting all of those, I will get the marginal. And by getting all of those, I will get the marginal for y. So we see this represented by a nice representation here. So this is how you can calculate, for example, the probability that x is equal to 1. And this is basically what we call fx of 1. Here's another that shows you how to do it for y. So this is the probability that y is equal to 4. And this is what we call fy of 4, right? And then you can do the same thing for all of them. You can get those probabilities. So this, what we see here, is the marginal of x. So the probability that x is equal to 1 is 0.2, x is equal to 2 is 0.25, x equals 3 is 0.55. This is the marginal distribution of x. And what we see with the blue color is the marginal distribution of y. So the probability that y is equal to 1 is 0.28. The probability that y is equal to 2 is 0.25. The probability that y is equal to 3 is 0.17. The probability that y is equal to 4 is 0.3. That's the marginal for y. This is the marginal of x. So you can see what we meant by the law, or the expression that we written. In order to get the probability of x at certain value x, this is equal to the summation of all possible values of y, f the joint, right? And you sum over all possible values of y. That's what we did, for example, to get this one. We went through all possible values of y. For x equals 1, we added them together, and the result was f of 1. Similarly, for f of 2, similarly for f of 3 to get the marginal for x, and similarly to get the marginal for, okay? Now, since we can get the marginal distributions or the distributions of the random variable x only by itself and the distribution for the random variable y only by itself, then definitely we can calculate the expectations for each one of them. How do you do that? From the joint, you start by, first step, calculate the marginal probability distribution. So you find the probability of the possible values of x, you find the probabilities of the possible values of y. Now you have the distribution for x by itself, you have the distribution for y by itself. We know how to calculate the expectations and the variance for x and the expectations and the variance for y separately, since we have the distributions from the definition of the expectations and variance. And that is shown here. So you calculate the marginals, that's the first thing. We get this and this, that was the first step. And then the second step is use the marginal, for example, to calculate the expected value of x. So value times probability, value times probability, value times probability added together. That's the definition of the expectation, right? Similarly, if you want to calculate the expected value of y, value times probability, value times probability, value times probability, value times probability, the definition of the expectation. Similarly, you can do the same thing for the variance using the definition of the variance and the marginal distributions, okay? Another important case, which was point number 3 in the introductory slide that we need to discuss today, is how to get the conditional probability from the joint distribution. So knowing fx, y of x and y, how can I calculate the conditional of the random variable x, for example, okay, given y of x and y, right? How can I get the conditional of x conditioned on a certain value of y? Sorry, typically we type the y here as small because it's conditioned on a certain value of y, right? How can I get the conditional distribution of the random variable x given a certain value of the random variable of y? The example here shows you how to do it, but before showing it in the example, we know that the definition of conditional probability is simply the joint divided by, this is what we call the marginal of A, right? The probability of A alone, the marginal of A, right? So we can apply the same thing for the distributions, because distributions, right, are simply, okay, probabilities. This is the probability that x is equal to the value x and y is equal to the value y, right? So distributions are just simply probability. So if I want to get the conditional, I'll just apply this rule. So what is probability of A intersection B? This is the probability of A and B. So A occurs and B occurs. So that's basically the joint probability that we called the joint distribution, right? Okay. So let's see, for example, assume that I want to calculate the probability that y is equal to 1 given x equals 3. Simply, this is equal to the probability that x is equal to 3 and y equal to 1. That's the first part. Divided by the probability that x is equal to 3, divided by the condition. That's the second part that we see here, right? So basically, this is simply the joint of 3 and 1. I can get it from the table that we saw in the previous slide, which is 0.25. And this is the marginal for x equals 3. I can get it also from the table where we calculated it at the end of the table, the marginal distribution for the case of x equals 3, and that's 0.55. So the result is that this conditional probability is equal to 0.45, right? I can also ask you to find the conditional of y equals 2 given x equals 3 and y equals 2 given x. So these are the y equals 3 given x equals 3 and y equals 4 given x equals 4, right? So you can actually continue doing these calculations. Have a look at the definition that we just mentioned, right? The conditional probability of the random variable y conditioned on a certain value of x, which is generally speaking a function of the random variable y, is equal, because we fixed x, so that's why the x does not show inside, right? Is equal to the joint of x and y divided by the marginal of x at the specified condition x. Similarly here, at the specified value of x, right? Again, this conditional probability by itself is a distribution, which means that if I sum its values, if I sum those conditional probabilities for a certain value of y, don't forget that we already fixed x because it's conditioned on a certain value of x. If I sum it for all possible values of y, it's going to give me 1, and its value is always greater than 0. And it specifies the conditional probability, right? Let's have a look. How can I, for example, build the conditional table for the random variable y given x from the joint table of the random variable of y and x together? So this one, we have seen it before. That's the joint distribution. And I want from that to calculate the conditional probability of y given all possible values of x. So the first is to calculate the conditional probability of y given x equals 1. How do you do that? Let's say we want to calculate, for example, the conditional probability of y given x equals 1 when y is equal to 4. So this one, this value, right? Not this value, sorry, this occurrence, the f of y given x equals 1 when y is equal to 4. The conditional of y equals 4 given x equals 1. By definition, this is what? This is the joint divided by the marginal of x. So we divide this number by this number by definition, right? When that is 0.75. So this is the first value. What is the probability that y is equal to 3 given x equals 1? Y equals 3 given x equals 1. That's the joint of 3 and 1 divided by the marginal of 1. And that will give you the value 0.1, right? What is the probability of y equals 2 given x equals 1? This is again the joint, which is this, divided by the marginal. So that will give you also 0.1. What's the probability that y is equal to 1 given x equals 1? All the values that we see here are conditional probabilities. So they are y equal to this value given this value of x, right? Again, it's this one, the probability of y equals 1 and x equals 1 divided by the marginal of x equals 1 from the definition. So that will give us this value. Similarly, we can do the probabilities for different values of y given x equals 2. That's what we see here. Okay. And similarly, we can do it given x equals 3. Okay. That's what we see here. Okay. So now we know how to calculate conditional from marginal. The remaining thing is to do something important. Notice that what we have in this table is a conditional probability. How do you differentiate if the table is conditional or joint if you are given the table? Simply, you can do this by looking at the table. If the sum of all the probabilities inside the table adds up to 1, then this is a joint table. If the sum of all the probabilities inside the table is not adding up to 1, then this is a conditional probability table. Now, which one is conditioned on which, you can figure it out by looking at the probabilities themselves. For example, here, if you add all of those together, in each column, they will give you 1. And this is the addition as you go through the different values of y. So this is the probability of y conditioned on x. Because for a fixed value of x, you add the values here, they give you 1. For a fixed value of x, you add the values here, they give you 1. If it was the other way, if it was x conditioned on y, it would have been when you add the values here, they will give you 1. Okay. You can also, as an exercise, try to build the f of x given y. Right. And keep in mind, these two things are not the same. F of y given x is not the same as given y. Okay. Now, if I want to calculate something called the conditional expectation, the expected value of y given a certain value of x, this is simply, again, since the conditional on x is a function of y, so the definition here is you multiply the value of y times the conditional probabilities for all possible values of y and you add them together. That will give you the expectation. Similarly, for the variance, this is called the conditional variance. You just simply calculate it from the conditional distribution. Okay. And this example shows you how to calculate the conditional. It's just an application of a numeric, like to the rules that we have mentioned. For example, if I want to get the expected value of y given x equals 1, then I go, this table is the conditional. This whole table is the one that we built in the previous slide, which is the f of y given x, right? That's the table. And I want to get the expected of y given x equals 1, then I'm caring only about those guys, right? Value times probability, value times probability, value times probability, value times probability. Add them together. They will give you the expected value of y when conditioned on x equals 1. What if it was conditioned on x equals 3? We would have done it using those set of probabilities and so on. Okay. Last but not least is the concept of independence. Two random variables are independent from each other if and only if, similar to the conditions of independence that we talked about for events, right? If and only if one of those conditions is true. Okay. What are those conditions? Either the joint distribution of both of them is equal to the marginal of the first times the marginal of the second, or the conditional of y given x is equal to the marginal without conditioning, or the conditional of x given y is equal to the marginal without conditioning, right? So if any one of those is true, then the two random variables x and y are independent. If any one of them is false, the two random variables are dependent, and it's enough to check one of them, as I mentioned before. So this is exactly the same as what we discussed in events, but we discuss it here on random variables. Okay. An important thing is when we look at the distribution of two random variables, the possible values of two random variables, if the possible values, so this is x and this is y, the set of possible values, if they don't form a rectangle, we know immediately by looking at the figure that they must be dependent somehow. If they form a rectangle, we need to check further whether they are independent or not. That's just a quick thing that allows you to figure out whether two random variables are independent or not. And here's an example of checking independence. You have plastic molding operation, and each part is classified as whether it conforms to the color and length specifications or not. So there are two classifiers. One says it conforms to color or not. We call that the random variable x. And the other one says it conforms to length or not, and we call that the random variable of y. It can be 1 if it conforms, it's 0 if it doesn't conform, right? Here are the x and y scatter plot. We call this a scatter plot. These are the possible combinations. It can be 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1 for x and y. Okay, and the values that you see there are the probabilities of those joint events. Okay, so this is, for example, the probability that x is equal to 1 and y is equal to 1, right? And so on. Okay, the question is, show me or test whether those two random variables are independent or not. One way to do it is calculate the marginal for y, calculate the marginal for x, and then check. Does the probability of x and y together for every possible value of x and y correspond to the direct multiplication of the f of x times the f of y or not? We can see here that this is the case. So for example, after calculating the marginals, and we know how to calculate the marginal from the previous examples, just by definition, summation. The marginal for x, you sum over possible values of y. The marginal for y, you sum over possible values of x. This is how we got those marginals, right? Okay. This is how we got those marginal values. Now to check, we need to see for x equals 0, y equals 0, the joint probability is 0.0002. And the multiplication of the two probabilities, x equals 0, y equals 0 from the marginals, will give you the exact same value. So they are here, yes, the same thing. Here, the same thing. This is equal to this times this. And here, this is equal to this times this, right? So it's true for all of them. This means that this condition, that the joint is equal to the multiplications of the marginal, is true, which means that they are independent. Another way to do it is by calculating the conditional, and in this case we did calculate the conditional of y given x, and then we see that it's the same. You will notice that this is exactly the same as f of y, regardless of these two are equal, and they are both similar to this. So this means that the conditional is the same as the marginal regardless of the value of the x. So that means that they are. By this, we are done with the material. I just wanted to show you that here, a quick comment that if we move to the continuous case, everything that we said applies, except that in that case, the probabilities becomes densities, and in order to calculate probabilities, you have to integrate. But the same things, how to move from marginal to joint and how to get the conditional and everything is the same, except that all those summations that we have seen before becomes integrations, right? So this is how, for example, you can get the marginals by integrating the joint rather than adding the joint and so on. So by this, we have finished the first part on joint distribution.